Thank you very much for inviting me to give a talk here. I'm going to talk about the method of resolution by weighted blowups, which was in particular done in the paper of Abramovich, the joint paper by Abramovich, Tomkin, and myself, and the similar method is also was conceived independently by McQuill and Marceau. But I'm going to talk about the results which were developed in this our joint paper from a different perspective, in a different language, in the language of torus actions. So those papers are written in the language of stacks and stack theoretic weighted blowups. And there are some disadvantages of this approach from my perspective, and that's why I would like to suggest a slightly different language and a different definition of the basic operations, which I will be calling a cobordant blowup. So let me explain you why we want to use weighted blowups, not smooth blowups. We know that Hironaka method uses smooth blowups, but these are very disadvantages. So the thing is, they really do not improve singularities, and in order to improve singularities, we need to introduce additional structure. So the proof is a combination of geometry and combinatorics and mixed together, which is something very conceptually difficult. And such a proof is also very, the method is because of that difficult to grasp and understand. So inductive steps are very simple, but if you want to combine them and understand what's really going on, it's not that easy. But the method which uses weighted blowups is very straightforward. If you look at the singularity, you see that we approach singularity from different direction at different pace. And if we use just a smooth blowup, then definitely we can improve singularity in one direction, but usually we make it worse in the other direction. So, and this is handled in the Hironaka-like proofs. This is handled by introducing this combinatorial structure, which kind of reflects that and compensates this worsening effect. So when we use weighted blowups, we only have a geometric tool, and the proof becomes suddenly very geometric. And combinatorics is hidden in the stack theoretic structure, and in my case, it will be hidden in the group torus actions. So let me start from a very simple example, which indicates that resolution could be sometimes very simple, right? So if you, let's say, if I have a simply homogeneous equation, fx1, xn, and suppose our singularity depends only upon the n variables, then what happens is, and we obviously then blow up the center, the smooth center. So this is homogeneous. We blow up center x1, xn. So let's consider the chart, let's say, associated with 1, 1. So y equals x1, and then y x2 is equal y x2. This is actually prime. Yeah, so anyway, xn equals y xn. Yeah. So xn prime and y are new coordinates, so maybe it's not classical. So what happens after blow up? We get, so this is homogeneous of degree d. Then we know that we get the equation y to the d f1 x2 xn in new coordinates. So clearly, the order drops, or the degree drops, right? So it's so simple, right? And then if I add here even higher order terms, so it's pretty general, higher order term. Then the same principle works, nothing changes. So if our world was so simple that everything would have been homogeneous, or homogeneous up to some higher order terms, then life would have been very nice and simple. And this is actually the case with weighted blowups, because we just think from that perspective on every single singularity. So suddenly every singularity becomes quasi-homogeneous. We just need to find the weights, right? So for instance, let's say the singularity is very simple. N1 plus x, or maybe A1, xn, an. This is actually pretty general situation. So that's exactly the same principle works in general. So we look at this type of singularity. Let's say it's isolated singularity, it doesn't matter. And then we introduce weights. We introduce integral weights. How we should introduce them? So you know, xi is some weight. It's weight wi. So it should be quasi-homogeneous. So w1 a1 should be equal to wn an. So now this becomes homogeneous with respect to this weight, and we would like to repeat the same thing for weighted blowup. So I will explain you how stacked theoretic blowup, what stacked theoretic blowup will give you, but the same thing will follow immediately from the complete formulas that I'm going to show you when we used torus section. So basically here, what happens with these weights, we blow up very funny ideals of fractional power. So x1, 1 over w1, xn, 1 to 1 over wn. Why this ideal? Why it's such a funny thing, and what is it? I mean, first of all, I would need to tell you that it actually will make sense, right? So, but why this ideal? Because the weight of this ideal is 1. The weight of all those elements is 1, and this is exactly as it's here. So the weight is 1. So this ideal becomes exceptional divisor, and it has weight 1, like before. And this also should have weight 1, and this should be transformed to exceptional divisor. So in the after weighted blowup, so this is a weighted blowup. After stacked theoretic weighted blowup, locally in the chart we have formulas that x1 becomes y1 to w1, and xn becomes x2 becomes a2 x2 prime y2 w y2 y1. I'm sorry, this is y. This is not y1. Y x2 prime y w2 xn ywn. So if we substitute this, that's xn prime. If we substitute this, we get exactly the same effect as before, except we need to factor out y a1 w1, and inside we have 1 plus x2 prime a2 2 plus xn prime an. Okay, so we see the same happens, and I could have replaced this with any possible equation. I would have the same effect. So you see that things becomes definitely better. But of course, one can ask, first of all, before going into the other things, what is this fractional power ideal? So in our paper, we call it evaluative ideal. And of course, I can imagine there are many different ways of giving a sense to fractional power, evaluative ideal. But one can think about this, for instance, from the following perspective. Suppose I have an ideal I, and so what is I to the 1 over n, naively speaking? I would just blow up this ideal, so blow up I, and what I see after that, I will see simply Q-Cartier ideal here. Inverse image of I is Cartier. I to the this fractional power is Q-Cartier. So we could think about evaluative ideals. There are several ways. One can say these are simply Q-Cartier divisors on birational modification, projective birational modifications. Equivalently, we could say that these are Q-Cartier divisor or on Riemann-Zariski space, if you really want to do this, because it may be convenient for some reason, but on Riemann-Zariski space. So this is a projective limits of all projective modification. Projective modifications. And equivalently, we could say that this is, we have on this RZ space, we have a sheaf O, and then we have a sheaf O star. So you could consider simply the quotient sheaf, or which is the side of the sheaf K star over star, where K is simply constant sheaf of rational functions, and we could just tensor it with Q. So we can think about a section of this form. So there are several ways of looking at this, and I don't have time to kind of compare those. But the thing is, every expression which involves ideals, elements, and their fractions could be just lifted to birational modification or to RZ space, and it will give some kind of Q-Cartier divisor or some section of certain sheaf. And now, having such a thing, so in our case, in my case, I'm going to consider this evaluative ideal of the particular form U1, A1, UK, AK. A1, Q. And such evaluative ideal, you could push it down, and it gives you actually also an ideal, right? So it will be just, if you have Q-Cartier divisor, you could consider obviously section of this divisor and push it down, and this will be simply the normal ideal, kind of normal. One can think about this as a normal closure. So for instance, a square root of u, the ideal of square root of u on x is just u, right? It's the upper integral part of it. of the integral closure. So this is the ideal on X. But the bottom line is it's really not important how to do it. The important is that there is a language of these fractional ideals, which is very convenient to use. Okay, because already in the definition, this evaluative ideal is involved, so if you have, for instance, if you have such an expression, you could obviously convert it into ideal on X simply by writing that this is generated by monomials u1 to the b1, uk to the bk, such that b1 over a1 plus bk over ak is greater than 1, greater than or equal to 1. So this is just a normal ideal, and this is just a convenient notation. And the thing is, with this evaluative ideal, you could multiply them, right? And then, for instance, if you take a power, then in this case, you just need to multiply all those elements, this equivalent. If you think about Q-Cartier device. Okay. So what I want to say, so now let us go back to, after this very short introduction to the topic of evaluative ideal, we can just say something, a few words about X, this ideal J of the form x1 to 1 over w1 xn 1 over wn. So evaluative ideal in this particular form. So we could associate with this evaluative ideal the graded ring AJ. This graded ring, I could write it in such a form, in the form of the evaluative ideal. So it will be just generated by JT. But this is a graded ring such that all the gradings are evaluative ideals. T is a dummy variable. And then I write X, which means that I am just consider the ideal of each grading, which is defined by the evaluative ideal, this sort of integral part as here. Right? So you have evaluative ideal, this fractional power ideal, and then when I write X, it gives me some graded ideal on X. And now this could be easily computed. This is the algebra which is generated by elements T to the AI Wi such that AI is, I'm sorry, Xi, such that AI is less than Wi. It's exactly what it is. So now we see that there is a one-to-one correspondence, so we could define now formally a weighted blowup in this language, and we could define a stack theoretic blowup, right? So this will be simply, so standard blowup is just simply a proj of Aj of this, and then stack theoretic weighted blowup, which again I won't be use it at all. Stack theoretic weighted blowup. It will be simply spec of this algebra Aj. Take away Vj. And we need to divide by stack theoretically by the action of GM. GM is simply torus. GM is spec K T T inverse. Right, so it's actually very similar than proj, but we simply take not a standard geometric quotient as normally, but we take stack theoretic quotient. But like I said, I'm not using stacks in this talk. Instead, I would like to rather look from the... I would like to... Oh, that's convenient. I see. It's not that complicated. Okay. So I would rather be using the notion of birational cobordism to look at this operation of weighted blowup. So let us recall definition of birational cobordism. So this is definition which was introduced for the proof of weak factorization theorem, birational cobordism. And this notion reduces the consideration consideration of the birational modifications simply to action of the GM. So it's a critical reduction of the critical.
Recording stopped.
Okay. Okay. That's convenient. I know. Yeah. Yes? Ah, okay. So this, what is it? Is let's say variety.
Sorry, what's the relation to stack blowup and weighted blowup?
Between stack theoretic blowup, that's yes. If you have a stack, you could take this coarse moduli space, and you get. So you could just take. This has more information. You could just take sort of additional quotient. You get exactly Proch, because Proch is spec AJ minus VJ. Okay. So these are related. It's simply, yeah, it's simply, there is
recording in progress.
There is more information in stack theoretic weighted blowup, and your space also becomes, your ambient, your space also is locally non-singular. So that's very convenient. So, and why birational cobordism? Because this is a language which was created to, for instance, in particular, visualize weighted blowups in a smooth way. So the thing is, this space, this algebra AJ, and spec AJ is not smooth, so it need to be modified accordingly. So what is a birational cobordism? It's a variety B with action of GM over, let's say, K, with action and action of GM, such that we have this upper boundary B plus is the set of all x, such that limit Tx as t goes to infinity does not exist. And similarly set B minus, but with t going to 0, these sets are open and admit geometric quotient. Geometric quotient. So what's the geometric quotient? It's a space of orbits. So we have B minus GM and B plus GM. So in this language, we could visualize weighted blowup. So this example, typical example is just we take T, acts on n plus 1. So simply T of x0, xn is T inverse of of x0, tw1 x1 twn xn. And if we draw a picture, it will maybe look something like that. Let me just make it. So this would be, so let's say the orbit go in this direction. So it will be, this will be the quotient. This is b plus. So all the quotient going to infinity, and this is b minus, roughly speaking. Yes. So of course there is a topological picture for the cobordism. It's like this is a well-known picture, right? So. And then you extend it to infinity, and then you see that you have those orbits, and this is upper boundary and lower boundary, except in algebraic geometry you don't use section, we just use the quotients. Right? So it's the same principle. Okay, so now this example now could be written in general as a definition of cobordant blowup. So definition. So first, a full cobordant blowup of X, smooth X, right? At this ideal J, which is locally described as x1 y to 1 over w1 xn y over wn, this kind of ideal is given by B equals to spec. So it's very similar to what is written on this blackboard, OX, but then we add T inverse, because this is exactly the same as visualization of this weighted blowup, T inverse, and then I have x1 tw1 xn twn. So suddenly, if I start from X smooth variety, my new variety B is still smooth. And these are new coordinates, actually. These are new coordinates. Okay, so let's see what happens to. Okay, so what is actually a cobordant blowup? So maybe trivial cobordant blowup. So maybe the cobordant blowup is B plus to X, right? So this will be, you need to remove, it's a B, we need to remove this V of x1 tw1 of the smooth, smooth subvariety. And then we also see that we have a trivial cobordant blowup, also trivial cobordant blowup, which is when we just consider B minus, and this is B minus this V of T inverse, and this is, by trivial I mean this is isomorphic to X times GM. Right, so we basically see what happens here by this very simple transformation. This transformation changes dimension and introduces the action. What does it do to our equation? Oh, first of all, what does it do to J? So let's see what happens. What is OB plus J? Right, so I would like to see this exceptional divisor here. And that's easy because OB plus J is OB plus, and here I write JT T inverse. But we see the thing is JT is actually, if you take a look at JT and you look at this, the power of JT is actually this. So we see that this GT is invertible. Invertible evaluative ideal. There always will be one of the coordinates representing this JT, which is a fraction of inverse function, the fractional power of inverse function. So that means that is just the T inverse, which is exceptional device. Exceptional device. So maybe it is worthwhile to draw a picture and also show the toric visualization of this. Because it's an operation, it is a toric operation in a sense, if we, for instance, start with toric variety, you get a toric variety. So it's okay, so let us see, let us draw a picture for this. So suppose I want to blow up a point on the surface, so how it will look like. So I will have a kind of maybe vibrations that generic fiber is an orbit. And the special fiber looks like this. We have orbit, we have the point, and we have this device. Oh, sorry. We are going actually in this direction. Yeah. Oh, sorry. Okay. So this is cobordant blow up. And what happens if I remove this part? Then it suddenly will start looking like this, like a blow up. So over this point, I will suddenly have the divisor. Okay, so maybe I also draw another picture of a toric situation. So it's a like I said, it's a operation which lives inside the also world of toric varieties. So suppose I have a toric example. I just draw a local picture. So the weighted blow-ups are very important in toric geometry or toroidal geometry, and they correspond to star subdivisions, right? So we just have a star subdivision. But in our language, it will look like this, that we simply lift this star subdivision up, adding one dimension more. So it will just project and the vector, which indicates the action, and this vertex will be projected to the center of the subdivision. And as you see, suppose I started from regular cone sigma. Then I produce a regular cone tau. So this is smooth world. Everything is smooth here. And if I want to see what is B plus, it will be tau plus. Tau plus faces of tau. Oh, maybe I should not be, because it's hard to erase. Faces of tau visible from above. Visible from above. Okay. Right. So this is a quite geometric operation, and let me show you how it deals with equations, right? So if we have equation of the form that, so suppose I have this example u1, no, x1, a1 plus xk, ak at the beginning. So, and then I consider this center J, which is x1 to 1 over w1, xk 1 over wk. So the new coordinates will be t inverse and t w1, x1, twn, xn. These are new coordinates. We see the old coordinates, so this is x1 prime, xn prime. So the old coordinates can be written as xn xi prime, which is equal to t to the minus wi xi. So actually it's opposite. So xi is equal to t to the minus wi xi. So if I just substitute for xi, this is xi prime, substitute for xi here, I get exactly t to the minus w1 a1, and then I have inside x1 prime a1 plus xk prime ak. So this is local equation on B. And that's very general picture. So what happens? I have this equation, and after cobordant blowup, full cobordant blowup, I have exactly the same equation. So what happens? But you know, the cobordant blowup is actually B plus. So now what I need to do? I'm just eliminating the singular point, because singular point is x1 prime, xk prime. So B plus is just simply B minus the singular point. So, and my singularity is resolved. And this is non singular. So this is what happens on the level of B. You get exactly the same singularity with exactly the same invariant, and you just remove it because it was the worst singularity. And after you remove it, you improved singularity. So, okay. How much time do I have, more or less? So,
15 minutes.
Okay. All right.
15 minutes.
15 minutes. Very good. So maybe I just, first of all, briefly formulate theorems, and then show a main invariant and maybe even some parts of the proof. The proof is quite short, but hopefully I will be able to. Say something. Okay, so in this language, you know, we simply have the following situation. So you have this non-embedded resolution. Oh, embedded resolution. I'm sorry. First, embedded resolution. And the method is so powerful that it actually gives you also non-embedded resolution by smooth weighted centers, because those simplification usually doesn't give that, the simplification of Hironaka theorem. Embedded resolution is more or less like that X be a smooth variety over K characteristic 0, and Y be some reduced subscheme and then there exists a sequence, of smooth of cobordant blowup, C blowups at centers, weighted centers, smooth weighted centers. Ji containing the yi. This is a strict transform. Of y. And so I have x0 equals x, x1, xn equals x prime, and then I have inside strict transform y0 is y. And then I have a group action. So at the beginning I have so Ti, which is n-dimensional torus, Gm to I acts on yi, xi, and everything is T equivariant. Ti acts on right, so xi to xi to xi plus 1 is Ti invariant, Ti equivariant. And then also, maybe I should write Ti plus is equal to Ti times Gm, because every time we perform cobordant blowup, we introduce the action of torus Gm, and such that first so everything is T stable. So yi also and Ji are T stable here. And finally, yn is smooth. Yn, the last one, is smooth. All right. And then, of course, one can say that if you want to look at from the point of view of quotient, or maybe, right, so this is a sequence of weighted blowup, standard weighted blowup on the singular variety with historic singularities. So, and also we have a similar formulation for stack theoretic blowup. So if you know this cobordant blowup, they contain more information than stack theoretic blowups. So like stack theoretic blowups contain more information than ordinary weighted blowups. And so I achieved a goal. My yn is smooth. And someone can ask, but of course, on the level of quotient, it's not smooth. But then, because what we did, you remember that Hironaka method is a combination of combinatorics and geometry, all mixed up together, which makes it difficult to think. But this method just separates combinatorics, which is hidden in the torus action, and geometry, which is hidden in the centers and the process. And the last part is to get rid of the singularities of these combinatorial singularities on the quotient. And this can be done, for instance, by, in particular, by my paper, or my paper on resolution of locally toric variety. And of course, in any characteristic, because these are combinatorial method, canonical resolution of locally toric variety. There are some stack theoretic results by Reed, which could be also used. But if you do not want to use stacks, you could, for instance, use this result. And so the main problem is always to reduce to, to reduce to this mild singularity. So these are singularities. The singularities of the quotient are really mild. So easy to handle. Okay, so and similarly we have non-embedded resolution by smooth center, so I'm not writing this down. You just need to have, I just say that I have the sequence of cobordant blowup. But at smooth centers contained in J. Sequence of cobordant blowup. By smooth centers by J, smooth, containing Y. So it's really a strong resolution. It's not, the centers are not normally flat, but they are smooth. Okay, so the next thing is, few words about algorithm, which is very simple. Algorithm is basically invariant. Invariant, right? So we introduce the natural invariant, which is actually reflects what I said before. We have a singularity, and you would like to understand the pace we approach this singularity from different directions. So that's exactly the definition. And so we introduce the following. Ideal on X, which is smooth. So we define invariant P I simply as maximum of all the sequences A1, AK. Here they are put in the ascending order, and these are actually rational numbers, such that our ideal I in the neighborhood of P is contained in this ideal U1, A1, UK, AK, this integral part. Maybe I should write P, formally speaking. So that's definition, and this tells me how fast I approach the singularity from which direction. And so you see immediately that that A1 is simply the order, and actually the whole definition, it's almost it's a very natural generalization of order. The definition of order looks almost the same, except here you have U1 and all the powers are equal. And then A1 is typically the order P of I. So, and then what happens is we can associate with any point P unique ideal. So this inf P is unique, and moreover, we have that this associated ideal is unique, this evaluative ideal, unique. And as I said before, it defines the center, which is J equals U1 to 1 over W1, UK 1 over WK, which needs to be blown up. After blow up, max invariant drops. After blow up, cobordant blow up at J, maximum of invariant drops. Okay, it depends how much time do I have left. I can say a few words about the inductive reduction, how to, well, I can say it in one sentence, or I could say it in 5 sentences, it depends. So is it, okay, all right, so the principle, because one can say that roughly speaking is the Hironaka algorithm, but highly simplified. So it is based upon the same principle. It's just a reduction, but in this case, of course, there is no logarithmic structure which messes up. So I only have, the only point is, so what we do here, we just reduce construction of this invariant for J to the construction of some coefficient ideal on lower dimensional hypersurface of maximal contact, where I have this invariant and all the properties. So I just lift all the properties from hypersurface of maximal invariant. So let's do this. So let's go to our relation. So this is what we have, right? And we are looking for maximizing this guy. So we can write this slightly differently as u1 and take u1 to the power uk ak over a1 to the power a1. Okay, because we would like to rewrite this inclusion in a language of graded algebra. So we see immediately, if you consider this is the ideal of derivation, I derivation, that it will be actually in this u1 uk ak over a1 to the power a1 minus I. So actually, I could rewrite it in terms of algebra, introducing dummy variable. So I have OX and the generators di I in the gradation t a1 minus I. And this is inside of the graded algebra of evaluative ideal u1 uk ak a1 t and x. So I have this reduction, and then what we see here, because it's a1 is the order, here in this graded ring there is an element which is called hypersurface of maximal contact u1, which is inside of day a1 minus 1, because in characteristic 0 taking derivative will cause the order drop by 1. So this has order 1, so it has a maximal contact. So if you see what happens, maybe let's call it x. So we see that x is actually inside of the also u1 here, u1 uk ak over a1 x. So it's easy to see that x could be chosen, that u1 could be chosen to be x, to be first coordinate. So we have a first coordinate. It's a maximal contact, which is from there. And now, once we have maximal contact, we could, so u1 is maximal contact, and we could restrict both sides. So after restriction, we see that we have OX, DII, this, let's call it this algebra R restricted to, and H will be our maximal contact. So we restrict R to H, both sides, and this will be now OH, because it just restricts like a usual ideal. U2, A2, A1, UK, AK, A1, T on H. So now the thing is, we could also go back. So if we take coefficient ideal, which is simply a factorial, maybe I'll have time even explain it why this one, then we see immediately, so this is called the coefficient ideal. Then we see that actually we have the following. CIH is contained in this, contained is this guy, OH. If and only if I is contained in our guy U, in our algebra R. Right? So, not our algebra R, I'm sorry, in algebra generated OX by U1, U2, A2 over A1. Okay. So now, this condition, and maybe this is the last thing I want to say. This condition means exactly that I have the Ci restricted to H is contained in, you could, in this U2, A2 over A1, UK, AK over A1, and this is in the gradation A factorial, A1 factorial, A1 factorial. This is U2 to the A2, U2, A2, UK, AK to the power A1 minus 1 factorial. And but now this is by induction given by some U2, B2, UK, BK, unique. And so I know those coordinates by induction. And it means I know those coordinates. And of course, I need to rescale those things. So this gives me that, so we can call it admissibility, that this condition for coefficient ideal immediately leads to definition to the condition that I started for the ideal I. So this basically modulo few lemmas finishes the whole proof that the condition I is translated on the condition on hypersurface of maximal contact, the same type of the condition. And we just translate it. Once I have this, I can leave this to, so U2, I know what's my coordinate U1, and I lift it to the center on I, and the proof is completed. Similarly, we do verification that after blowup, cobordent blowup, invariant drops because it drops on the hypersurface of maximal contact. So it drops, and it drops for the ideal, original ideal I. All right, that's all. Thank you very much.
Yeah. Thank you for your talk and to show that. Are there questions? Quick questions?
You said torus action in your title, but I understood in the talk you only having a C star acting.
At the beginning, I have a C star. No, I mean, what do you mean? Here I have, at the single blow-up, I introduce C star. But in the multiple blow-ups, of course, I need to have a torus action because the torus action accumulates at each step.
Okay, I see. Thank you. And a side question to that one, the torus action, is that a choice?
No, it's kind of canonical. It is canonical action because, you know, look at these coordinates. This is, it is introduced in the definition of cobordent blow-up. There's some dummy variables T, which suddenly becomes no.
Oh, it's the action on the T variables.
Yes, it's simply the action of T on itself.
But then the choice of generators over the ideal is a choice or something.
No, there's no choice in, because it is really about algebra. Algebra is independent upon the choices. Yeah. So of course, description is dependent, but this is about the algebra. Algebra AJ, and this algebra AJ is uniquely associated with valuative ideal.
I see, thank you.
Thank you. Are there any other questions?
Is there a way to keep track of all these invariants at each step? Some point keeps them as some Functorial invariant?
To keep track of all the, I mean, you don't need to keep track of the.
I understand that you don't need for your algorithm. Somehow, in order to get some information about this invariant.
So, I mean, so your question is whether, your question is there the way to keep all...
Well, so some sort of much more defined invariant than the order of it.
Yeah. Yeah, I mean, I cannot answer right now, you know, because I don't quite completely. I don't completely understand your question. I mean, you know, we will talk about this later. So.
So the
One can say that. You know, it depends how to look at the things. You know, philosophically, there are in characteristic 0, there are just toric, this weighted blowups and toric valuation, which are essential. And in characteristic 0, characteristic P, formally, we have problem with maximal contact, but also there are some sort of group actions, and there are different type of valuation which need to be taken in account. So it's not so easy to, I mean, for instance, this kind of minimal, this is not unique in characteristic P. There are many of them. And if you just choose a point that it does not behave, I mean, it doesn't make things worse because it's, you know, but it doesn't improve the situation. You will have infinite loop. But yeah, so, but this agrees with Abiancar philosophy that you cannot just, you know, if you choose a bad point, you cannot just resolve singularity at arbitrary bad point by using simple invariants, which, you know, which rely on some initial forms or order some simplistic invariant, because it would lead to very simple description of ramification and other phenomena. So there are some obstacles, obviously, but and there are obstacles of different nature in positive characteristic. But this is a tool that you could apply to any algorithm that you like, existing or future algorithm, and it makes things much faster and simpler. You remove conceptually lots of difficulties associated with smooth blowups. Wherever you use smooth blowups, you can forget them. You just use those, for instance, coordinate blowups, and your equations suddenly become very simple immediately. If you compare the method, it gives you sometimes 2 blowups. Traditional smooth blowups gives you hundreds of blowups, you know, for the same equation. So that's how it works. Okay.
I'm afraid we have maybe, I don't know, we have not much time for more questions. I think it is because the next talk we must start at once, I think within 1 minute. So maybe we can go on with questions after then. I think we can thank the speaker again. Thank you.